Today we're going to talk about capacitors, our first of the electric circuit elements. Capacitors come in all shapes and sizes. Here's a few examples, some small ones, some large ones here. This particular one is used for time travel. The basic way to build a capacitor is to start with two hunks of metal and just remove charge from one of them and move it to the other one. So here, this left side is positively charged, the minus side is the right side is negatively charged. This is a capacitor. It's basically, we've spent energy to move charge from here to here, and there's energy stored in this system now, and there's an electric field between them, right? The positive side has electric field lines that are coming out of it because positive charge creates electric field lines going away from it, and then the negative side has electric field lines going towards it. So equal and oppositely charged pieces of metal. That's the basic, most simplest concept of a capacitor. If you want to look at one sort of more formally, this capacitor is a parallel plate capacitor. Two plates, each area A parallel to each other, separated by a distance d. The top one is positively charged, the bottom one is negatively charged in this case. So here's what it looks like from the side with the electric field lines. So we have positively charged top, negatively charged bottom. So there's electric field lines going from the top to the bottom. And the electric field line created by one sheet of charge is sigma over 2 epsilon naught. Since we have two oppositely charged ones, then they actually reinforce each other inside, and you end up with the total electric field inside to be twice that. So the electric field between those two plates is sigma over epsilon naught. Now, how do we define a capacitance of a capacitor? A capacitance is a measure of how strong a capacitor it is. Well, one way to do it is to say that the charge on either side, Q, is equal to C times V. This is a measure of how well this thing can store charge. If I were to solve this for C, it's equal to Q over V, and you can think of this as, this is how much charge I can get on this capacitor for a given voltage. The more charge I can get for a given voltage, the better the capacitor is. And so, units of capacitance, so it's coulombs per volt, charge per voltage, and we're going to call that farad, named after Mr. Faraday. Let's just do a simple, really straightforward calculation here. We have a wrench with charge plus 70 picocoulombs on it, and a saw with charge minus 70 picocoulombs on it. And we're told that the voltage difference between these two things is 20 volts. So we have everything we need here. The voltage is 20 volts. The charge on either side is 70 picocoulombs. So we can calculate the capacitance. The capacitance is going to be Q over C, or Q over V. So Q is 70.0 picocoulombs. V is 20.0 volts. And so if 70 divided by 20 is 3.5. And coulombs divided by volts is farads. And let's just leave the pico there. That makes it easier. We end up with 3.5 picofarad. Next question asks, if the charge was increased to 200 picocoulombs and minus 200 picocoulombs, what would be the potential difference? Well, the capacitance stays the same. The capacitance is a property of this particular arrangement. So the capacitance will always be 3.50 picofarads until we change it, right? And the new charge on it is 200 picocoulombs. So if I use this to calculate the new voltage, so the voltage is going to be, in this case, just flip that equation around, Q over C, and we plug it, we get about 57.1 volts. In order to help us study the properties of capacitors, we're going to introduce the concept of a battery. You know what a battery is? Here's a basic, common looking battery. And for us, for our purposes, for now, let's treat a battery as just having one job. One damn job. Its job is to maintain the potential difference between its two ends. This particular one will try to maintain a potential difference of 1.5 volts across its ends. So what it does is it moves charge to one end, removing it to the other. It raises that charge to a higher potential such that the potential difference between these two things is 1.5 volts. Okay, and it does so by converting chemical energy into electrical energy. And we'll get into the details of batteries a little bit later on, but a battery maintains a potential difference of 1.5 volts by distributing charge. Another way to think about it is that it delivers power. And we'll get to power a little bit later on. So we're going to come up with a system for schematically representing what these things look like. So here's, a car battery attached to two huge metal plates separated by a distance, and these two plates are representing a capacitor and attached to a switch. So the battery will often be represented by this symbol here, a short line for the low voltage or the negative side, and a longer line for the positive side or the higher voltage. So this is usually at a higher voltage than this side, and that represents a battery, and there's always a potential difference across here. So this is trying to maintain a potential difference of V between the top and the bottom. And this is, the capacitor is drawn as a little parallel plate capacitor, and the switch kind of looks like a little switch, and it's usually connected by wires. So what happens when you close the switch? Well, the battery's trying to maintain a potential difference, right? So it's going to charge up this capacitor positively and this side negatively to maintain a potential difference of V across the capacitor. That's basically what it does. Now, how do we calculate the capacitance for a particular parallel plate capacitor? So if we have a parallel plate capacitor, it's two plates, each with area A, separated by a distance d, and they have equal and opposite charge of plus and minus q. Well, remember I argued earlier that the electric field is sigma over epsilon naught between these two things. So given that the electric field is sigma over epsilon naught, we can write sigma, that's the surface charge density, it's charge per unit area. I'm going to plug that into here and then solve it for Q. So if I solve this for Q, I get Q is equal to epsilon naught E times A. Now the reason I solve it for that is because I want to find the capacitance, right? So Q, in terms of the electric field in the area, I'm going to plug that into here. Now, the voltage between them, well, when we did our voltage section, we saw that for a uniform electric field, the voltage difference from one plate to the other is going to be the uniform electric field times the distance between them. So I'm going to plug Q into here, and I'm going to plug the voltage into here, and you'll see that the electric fields cancel out, and it simplifies down to this expression for the capacitance due to parallel plates. The electric field, the capacitance gets larger the larger the plates are, and the capacitance gets smaller the larger the distance between them. I have a simulation to show this relationship. Here's a little simulation to help us visualize what's going on. I've got a battery attached to these two parallel plates. They each have a separation and a plate area. So if I turn on the battery here, you notice that this side becomes positively charged and this side becomes negatively charged. I can add my little fake voltmeter, measure the voltage across from one to the other, and it's 1.5 volts. Okay, so now I can calculate the capacitance, right? The capacitance in this case is 0.89. That's based on that equation we just saw where it's epsilon naught A over D. Now if I move the plates closer together, see the capacitance goes up. The voltage stays the same because it's attached to the same battery. It doesn't actually change the voltage. The capacitance goes up because they're closer together, and when we think about it, is when they're closer together, the electric field gets strong. There's more electric field, so there's more energy stored. Okay, so when they're closer together, you get more charge. If I have larger plates, I can store more charge on them, and the capacitance goes up again. I have to zoom out here. If I shrink the plate, the capacitance goes down. Here's a simple example. I have two parallel plates. They each have an area of half a square meter, and they're separated by let's make it a millimeter. They're each separated by 1 millimeter, and they are charged up. So this plate has a charge plus Q, and this plate has a charge minus Q, which is, and the Q is 5 microcoulombs. So if you remember, a microcoulomb is 10 to the minus 6 coulombs. Just as a reminder, is 10 to the minus 6 coulomb is what a microcoulomb is. Now, we can easily calculate this capacitance. The capacitance is epsilon naught times the area over D. So if I plug in for epsilon naught, it's 8.854 times 10 to the minus 12 farad per meter is one way you can do the units, times the area, 0.500 meters squared, divided by 1.00 times 10 to the minus 3 meters. And if you look at the units, the meters all cancel out, and I plug everything in, I get approximately 4.4 times 10 to the minus 9 farad, or about 4.4 nanofarad. So that's the capacitance for this particular arrangement. If I move the plates closer together, the capacitance increases, and so on. So, next let's talk about some particular arrangements of capacitors. Okay, so if I have here 3 capacitors attached in this particular situation here is called 3 capacitors attached in parallel. So here's capacitor 1, capacitor 2, capacitor 3 attached to a battery, and we're going to represent the voltage of this battery. This is a EMF, but we'll use the letter E sometimes to represent the voltage. So these 3 capacitors are attached in parallel to this battery. What's the equivalent capacitance of this whole circuit? So sometimes you'll have a circuit with lots of capacitors in it, and you want to know what's the equivalence, what's the equivalent single capacitance of it. So these 3 are in parallel because the battery is attached across each of them individually, if you look at it. Here, these 3 are attached in series. So the battery is attached to one, and then the voltage across all 3 of them is equal to this E. So we're going to look at the situation for what's the equivalent capacitors when I have 3 in parallel or 3 in, or any number in series, parallel and series. So if I have attached this battery to these 3 capacitors, what is their equivalent capacitance? Well, let's start by saying that the battery is going to send out some positive charge this way and some negative charge this way, right? And what happens to this charge? Well, it's sending charge out, and some of it's going to go onto this first capacitor, some of it's going to go onto this one, and then the rest of it's going to go onto this one. So you're going to have positive charge on this side. This will be, plus Q1, and then minus Q1 on this side. This will become positively charged, this will become negatively charged, and there'll be Q2 on this one. This one will become positively charged, this one will become negatively charged, and it'll be Q3 on that one. So the charge on each of those is, the charge comes out of the battery, some of it goes onto each of the 3 capacitors. So how can we use this to find the equivalent capacitance of the whole thing? Well, let's start with the fact that the total charge that comes out, Q, has to be equal to Q1 plus Q2 plus Q3, right? Some charge comes out and it splits between these 3, not necessarily evenly, it depends on the capacitors, but if I add up these 3 charges, it has to be equal to the charge that comes out of that battery. Now let's compare this to what we're trying to find. We're trying to find an equivalent capacitor. In other words, if I rewrite this battery like this, I would like to be able to rewrite this circuit as just one capacitor. So this is going to be my equivalent capacitor. And remember, this thing sent out plus Q. So positively and negatively charged Q is on here. So what I'd like to be able to rewrite now for each of these capacitors, I'm going to use the equation that C is equal to Q over V. That's our definition of capacitance. Or I can rewrite it as Q is equal to CV. So I can plug in for each of these. So Q is going to be equal to C equivalent times the battery voltage, which is E. That's going to be equal to, for Q1, it's going to be C1 times the voltage across this. Now here's the trick. Remember this battery? It maintains a voltage of E from here to here. And that means the voltage from here to here is E. So the voltage across this capacitor is E, because that's what a battery does. It's trying to maintain every point here at the high voltage and every point here at the low voltage. So the voltage across this is E, which means the voltage across this one is also E. The voltage between any point here is the same. It's going to set this at the high voltage, and it's going to set all this at the low voltage. So this voltage here is going to be E. And then it's going to be plus C2E plus C3E. So the voltage across each of these things is E for all 3 cases. Now if you look at this, The E's are going to cancel out. And we get that C equivalent is equal to C1 plus C2 plus C3. And that's our final answer, is the equivalent capacitance of the whole thing is just the sum of the individual capacitors. One way to think about it is this battery provides a voltage across here of E, and so it charges it up with Q. And it provides the same voltage across here, so it's going to charge it with Q2. And it provides the same voltage across this, so it's also going to charge up with Q3. So the total capacitance of adding 3 capacitors in parallel is you just add those 3 capacitors together. So let's do sort of a, so that's the general equation for the capacitance. Let's do an example of adding capacitors together in parallel, just to give you an idea. So let's say here that I have a battery, like so. And let's say, just for fun, this battery is 24 volts. And it is attached across 2 capacitors that are in parallel. So you see how this is also in parallel. I'm going to call this capacitor here, I'm going to call this capacitor C1, is going to be 6 microfarads. And C2 is going to be 3 microfarad. Alright, so we have a battery attached across 2 capacitors, and I want to be able to rewrite that as a single circuit. So if I want to combine those two, so the battery stays the same, and I want to combine those two into a single equivalent capacitance. And for adding 2 capacitors in parallel, that's just going to be equal to C1 plus C2. So it's going to be equal to 6 microfarads plus 3 microfarad. So the equivalent capacitance is 9 microfarad. So in other words, attaching this battery to 2 capacitors in parallel that are 6 microfarad and 3 microfarad is the same as if I were to attach the same battery to a single equivalent capacitance of 9 microfarad. And we'll see pretty soon why we care about that. What if I add them in series? Well, then I have a slightly different situation when I add them in series. Let's think about it. Here, again, if I attach it, it's going to send out plus Q that way and minus Q that way, right? And that plus Q, if you follow it along, it can only go here. So all the charge, positive charge, has to go Q there, which means the bottom will pull minus Q up here. The minus Q here all goes here, so this will also be charged minus Q, and this will pull down plus Q here, which will pull it from there, and so on. So the charge on on all 3 of them is going to be Q. And once again, it's because plus Q all ends up on the top side. So and the minus Q all ends up on the bottom side of this one. So this one wants to be canceled out, so it's going to pull plus Q so that they have equal and opposite. And at this plus Q, it pulls it down from here, so this becomes minus Q. This positive Q pulls minus Q up, and it pulls it from here, so this becomes plus Q. So the charge on each capacitor ends up being the same. Now, to figure the rest out, the voltage from here to here is E. That means that the voltage from here to here is also E. Okay, so the total voltage across that whole thing is E. But the voltage across, so the voltage, if you go from here to here, the change in voltage should be equal to the change across the battery. But it's going to be a different amount for each battery. So for each capacitor. So the voltage across this one will be 1, and then some more voltage will be across here, and then some more voltage will be across this one. So we can say that the voltage across the whole battery is going to be equal to the voltage of 1 plus the voltage of 2 plus the voltage of 3. Remember, the voltage from here to here is going to be the same either path. If I go this way, it'll be E. If I go this way, it'll also be, or it'll be minus E. But the voltage from there to there has to be the same. So they have all the same charge, they have different capacitances, and they all have different voltages. Well, I'm going to use my definition for C, right? Remember, I'm going to use that C is equal to Q over V, or rewrite that as V is equal to Q over C. So, remembering that I want to rewrite this whole thing as some battery attached to some equivalent capacitance with charge Q on it, right? And voltage E across it. So, this becomes here Q over C equivalent for that, and that's due to the equivalent capacitance. And then V1 becomes Q over C1, and V2 becomes Q over C2, and V3 becomes Q over C3. And the charges all cancel out there, and we get our final equation that 1 over C equivalent is equal to 1 over C1 plus 1 over C2 plus 1 over C3. And it's all due to the fact that they all have the same charge on each other, and they're attached in series like this. And so our equivalent capacitance for that that whole thing is you sort of add them inversely like this. So let me do sort of a simple example. Well, let me do the same two capacitors as before, but this time we're going to place them in series. So if I have that 24-volt battery right here, here's my 24-volt battery, and I attach it to two capacitors in series, like so. And from before, those two capacitors, C1 is 6 microfarads and C2 is 3 microfarad. And I'd like to rewrite this as an equivalent 1 capacitor, like this. C equivalent. Remember, C equivalent, the equation is right here. It's 1 over C equivalent equals 1 over C1 plus 1 over C2. So I'm going to do 1 over both sides. And so C equivalent is equal to 1 over C1 plus 1 over C2, which is 1 over 6 microfarad plus 1 over 3 microfarad. When you work it all out, works to 2 microfarad. So that's the equivalent here. So when we add two capacitors in series, they have an equivalent capacitance of a lower, crappier capacitance. The capacitance actually goes down. Here's a couple multiple choice questions. I will read them out and then give you a second to think about them. The equivalent capacitance of these two is what? Now, it's the equivalent capacitance between here and here, so if you look carefully, these two are in parallel because the voltage can go either this way or this way. So these two are in parallel, so the equivalent capacitance of these two will be 9. When they're in parallel, you just add them directly together. So if I attached a battery to this, it would charge both of them up with the full voltage. How about this next one? The equivalent capacitance of this one is, well, these two are in series, so you'd have to do it similar to the one we just did, right? So that one, the answer would be, the answer would be 2 microfarad. Because you add the sum of the inverses and then it inverse that. This example here, it's 2 in series again. So what's the answer to that one going to be? Well, you just add them directly together. Sorry, they weren't in series. They were parallel. So when they're in parallel, you add them together and you just add them directly. Parallel because go through one, then go through the other. Here, rank in order from largest to smallest the equivalent capacitance of each of these circuits. So here's an easy one. This one, it's just going to be 5 microfarad. These two, if you look at it, it's 2 in parallel, right? When 2 in parallel happen, you just add them directly together, right? So it's parallel, so you just add them together. It's just 2 microfarad. So one shortcut to remember is when you have two identical capacitors in parallel, since you add them, you're basically just doubling the capacitance. Right, you just double 2 times 3. And if I have 2 in series, like this second one here, these 2 in series, you do 1 over 3 plus 1 over 3 and then 1 over all that, you end up with 1.5 microfarad. So when you have 2 in series, you actually cut the capacitance in half. So remember that. Two identical ones in parallel, you add them. Or you multiply them by 2. Two identical ones in series, you cut them in half. Now here, it's a two-step process. We have to add them individually. So these two are in series. We can add those at first. The equivalent of these, remember, it's going to be 1 over 4 plus 1 over 4. So that would be, you have two identical ones, cut them in half, you get 2 microfarad. Then I have a 2 microfarad in parallel with a 3 microfarad. So this becomes 5 microfarad. All right, so the largest one will be B, and then the next largest will be A, which is the same as D, which will be greater than C. So I'd like to do an example problem. Here we have a circuit. It's a 10-volt battery attached to 2 capacitors that are in parallel with each other. And the question asks, for the circuit shown, find the charge and voltage across each capacitor. So we want to find out how much charge is on each capacitor and what is the voltage across each capacitor. Now the way to do this, or one way to do this, there's other ways, but one way to do this is to first, we want to reduce it to an equivalent circuit. So remember, an equivalent circuit would mean we want to replace those two capacitors with a single equivalent capacitors. A single equivalent capacitor. And the equivalent capacitance, C equivalent, right, will be it'll be C1 plus C2. So you just add the two capacitors together, right? So the two capacitors add up to, that's nice and easy, 20 nanofarads. So now that we know this thing here is 20 nanofarads, so this is 20 nanofarad. Nice and easy. Next, what we want to do is we want to find the charge. So remember I said an equivalent charge is going to come out of the top and the bottom. It'll be plus one side and minus Q on the other side. So what is Q going to be? Well, to find Q, let's just use our equation, right? Q is equal to CV. We want to find the charge across that thing. What is the voltage across this capacitor? To find the charge, we need to know the voltage across it. Well, it's attached to a 10-volt battery, and it's the only capacitor for this equivalent capacitors, right? So the voltage across this thing is 10 volts. So we have 10 volts, we have a 20 nanofarad capacitor, so we can find the charge on that equivalent capacitor. It's going to be 20 nanofarad times 10 volts, so we end up with 200 nanocoulombs. So that means 200 nanocoulombs comes out here and minus 200 comes out there, and it's going to spread itself evenly between those two capacitors, right? Some of it is going to go this way and the rest of it's going to go that way, and we can easily figure that out. We can let's see, we can find the voltage on this thing is 10 volts, and once again, when these two are in parallel, so the voltage from here to here is the same as the voltage from here to here. Once again, the voltage from here to here is the same as the voltage from here to here. The voltage between any 2 points is going to be the same if you don't cross any circuit elements. The battery is going to maintain this voltage to be the same as that voltage the same as that voltage. So it's going to be 10 volts across these things. The voltage across two things in parallel is always going to be the same. And since we have two of them, in both cases we can always find Q using C times V. So Q for the capacitor on the left, it's going to be 17 nanofarads times 10 volts, so it'll be 170 nanocoulombs. And this will be 3 on the right hand side, it'll be 3 nanofarads times 10, so it'll be 30 nanocoulombs. And there you have it. We have the voltage and the charge on each of these things. And that is equivalent to what we found here, because we said that the equivalent capacitance was, the equivalent charge was 200 nanocoulombs. And that makes sense. 170 plus 30 is 200. So 200 came out. Most of it went onto the bigger capacitor, and some of it went onto the lower capacitor. Well, let's do another one with 2 capacitors in series. So just like the first one, but a little bit different. So we want to be able to rewrite this as a single circuit again, right? So we'd like to be able to combine those two in series into one single capacitor, like so. So we have this original voltage is 24 volts, and we want to find C equivalent. Now C equivalent, because it's 2 in series, it's going to be 1 over 12 plus 1 over 6 microfarads. When you work it all out, it works out to 4 microfarad. So this is a 4 microfarad capacitor, the equivalent capacitance. How much charge is going to come out? Well, to find the charge, Q, we're going to use Q is equal to C equivalent times V. So the C equivalent is 4 nanofarad and the voltage is 24 volts. So 4 times 24 is 96. We're in microfarads? Yes, microfarads. So 96 microcoulombs. So that is Q that comes out here. It is 96 microcoulombs. That means because these are in series, all that charge, it can only go one place. It has to go onto here. 96 microcoulombs. And the minus Q is going to come over here. And so remember, this Q represents the positive and negative amount. So we just use the positive value. So they have the same charge on each of them. They're going to have different voltages though. You can calculate the voltages using Q over C. So the voltage for 1 will be 96 divided by 12. Okay, and 96 divided by 12 is 8. So we have 8 volts on this one. And V2 is going to be 96 divided by 6. And that works out to be 16 volts. Right, so we have the results for the second capacitor and the first capacitor. Now, do they make physical sense? Remember, this voltage maintains a voltage difference across this whole thing to be 24 volts. That means the voltage from the top to here has to also be 24 volts. And it is, because the voltage across this one is 8. So that's a voltage difference of 8. And then the voltage across this one is 16. It's another 16. So the total voltage from here to here is 24. And this is sort of highlighting the differences between voltage and charge and capacitance. So one final example where we combine parallel and series together. The trick to this, so here if I want you to find the charge and the potential difference across each of these 3 capacitors, the first step is reduce it down to a single capacitor. And you can do that in just a couple steps. The first step you want to do is find 2 that you can definitely add together easily. Well, you see that C2 and C3, these 2 are just in parallel with each other. So I can rewrite this circuit as, there's the battery, there's the C3 from before, or C1 from before that hasn't changed. But if I add 2 and 3 together, they are in parallel. And adding 2, so this is C like 2, 3. And you just add them directly together. That is 6 microfarad. And that one is still 3 microfarad. So we've added those 2 together. So that was the first step. The second step is adding those 2 now that are left, C1 and C23, into one equivalent capacitance. All right, and the equivalent capacitance for adding 2 in series, remember, is 1 over C1 plus 1 over C23. And when you work that out, we did something similar before, you end up with 2 microfarads. So the equivalent capacitance of the whole thing is 2 microfarad. We have this 12-volt battery here. So we can find the equivalent charge that comes out using that. So remember, using Q is equal to CV. So 2 microfarads times 12 volts. So the total charge that comes out is 24 microcoulomb. So now I can use that to start filling in the blanks back here. So we know that 24 microcoulomb comes out of this. So that means it all has to go here. This is 24 microcoulomb. It has to be all 24 microcoulomb. And when it comes, and you know, the minus 24 microcoulomb comes out here, and it's going to charge out these 2, but it's going to split between those 2. We're going to figure out the rest of that in a second, but first, since I know for this capacitor, since I know the capacitance and I know Q, as soon as I know 2 of them, I can find the third one, right? I use V equals Q over C. So now V1 is going to be 24 microcoulombs divided by 3 microfarads, so the micros cancel each other out, and I end up with 8 volts. Now here's the trick to solving this one. We know that the battery is 12 volts from top to bottom. That means from here to here, it's 12 volts. From that top to the bottom here, it's 12 volts. And it's 12 volts regardless of the path. So it's 12 volts this way, or it's 12 volts that way. So if this is 8 volts, then the difference for the remaining part has to be 4 volts, because it has to add up to 12. So if that's 8, then the remaining must be 4. So that means V3 is 4 volts, and V2 is also 4 volts. Okay, so now we have the voltage across and the charge across. We have the voltage and the capacitance across these two, so we can find the charge across each of them. So the charge for this one will be 4 volts times 5 microfarads, and I end up with 20 microcoulombs. And then this one, Q3, it's 4 times 1, so I end up with 4 microcoulombs. And everything checks out. Does the voltage from the bottom to the top, is it add up to 12 volts? Yes, because it's 8 plus 4 this way, or even 8 plus 4 this way. Do these two charges add up to 20 coulombs? Yes, because minus 20 came up here, so the bottom became minus 20, and the top would be plus, minus 24 came out. And so the bottom becomes minus, the top becomes positive, so the charge is 4 and 20, that adds up to 24. Same as the charge there. So everything is nice and simple. Here's sort of a slightly prettier version of what I just did.